Good morning or afternoon, wherever you may be. My name is Andy Deal. I'm your host today. Thank you for joining us on our webinar. So today we have a special guest, Isabel Sanz from HP. She's an inventor. She holds, I think, 10 patents. She's an author, a speaker, and an evangelist for anything that's 3D printing. So she's a very, very busy person, as you can imagine. So thank you very much for being with us today, Isabel.
Sure.
So today our agenda is fairly simple. I'll talk a little bit about Saratech and share with you what we do as a company. But the main portion of the presentation, Isabel will be sharing with us how to customize products efficiently at a lower cost and with minimal waste using HP 3D printing technology. So if you think about it, mass customization is applicable for many industries. Matter of fact, customers now demand customization a lot of time for the products that we produce, right? So, whether it's automotive, consumer products, or medical, people want things to be customized. So as you watch some of the examples that will be shown today, think of how they apply to what you do, to your company, and to your industry. Obviously, we expect some questions to come in. So at any time during the webcast, if you have questions, please type it into the chat box of your GoToWebinar panel, and we will address the questions in the Q&A portion of the webcast. Before moving the presentation over to Isabel, I just want to take a minute to introduce you to Saratech if you haven't been with us before on a webcast, and also to reintroduce you to Saratech if you have been with us on a previous event. So Saratech is an engineering organization. We focus on helping customers optimize design, analysis, and manufacturing processes. We've been around since 2002. We have over 90 dedicated professionals working here, and over half of which are actual degreed engineers. So we earn the trust of our customers by delivering results and building great relationships. We're headquartered in Orange County, California, but our team is located throughout the United States to best support our customers all across the country. So with that, I now pass the presentation over to Isabel. Isabel, all you.
Yeah, good. Yeah, so thanks, Andy, for the introduction, and yeah, thank you everyone for taking the time to attend this webinar today. Oh, I'm going to start sharing my screen. One moment. Good. So yeah, as Andy said, I'm Isabel Sanz. I'm working as a 3D applications engineer in HP, and I cover the West Coast and Mexico. So my role in HP is to help the customers to identify part candidates that we could move to production. And in order to make it happen, I validate with them the full end-to-end workflow, which includes redesign considerations to get the optimum designs with multi-jet fusion, printing settings such as the parts orientation, for example, or the packing density, and then final post-processes if that's required, and quality management systems. So today, I'd like to share with you which are the best opportunities and applications that you could move to additive manufacturing, and which are the benefits that could be obtained through that process, including, for example, competitive advantage in terms of cost, additional performance achieved, and many others. Then afterwards, I'll give an overview of multi-jet fusion and how HP's technology is enabling these manufacturing capabilities. And finally, I'll also review some success stories of customers that are using today multi-jet fusion for production in different industries, with a special focus in industrial equipment and in applications in the medical market, such as prosthetics and orthotics. Good, so yeah, let's start with the 3D printing opportunity. But first of all, before we start to deep dive in the specifics, I'd like to give you an overview about how the manufacturing industry is changing today due to the introduction of the additive manufacturing technologies. The rules of the game, the rules of manufacturing are changing, which will bring new scenarios and opportunities in the following years. For example, we see a trend from the mass production that started at the beginning of the 20th century, and now there's a mega trend that moves us to mass customization. The customers look for unique products and they look for personalization. Then, on the other hand, from the trend of placing the production overseas, we move to distributed production, which is able to be more flexible to meet shorter lead times and therefore adapt faster to variations in the demand. And even if we take a look into the supply chain, there's a movement from storing parts to produce parts on demand instead. And this will lead to store files instead of storing parts, which will contribute to the reduction of the inventories and warehouses. And if we run the comparison with other traditional manufacturing methods, we can see some evolution as well in the mindset to design for each of those. When we design for CNC machining, we try to reduce the machining operations. And now, instead of looking into that with additive manufacturing, we'll think about how to minimize the material used. This is the biggest and the main change that happens when we move from a subtractive technology to an additive one. A cost-effective part in a subtractive technology, such as CNC machining, for example, will be a very solid part, as the cutting operations of the part are reduced in order to minimize the cost of the part. Because if the part is taking longer to be produced, that means a higher cost. But in additive manufacturing, the approach is totally different. A part will be designed in this case to have the minimum material needed in order to be more cost effective. And this also has advantages in terms of CO2 reduction, as it's more sustainable because we have less waste material. Then in the same direction, if we compare it with injection molding, instead of thinking about the demolding directions in the mold and the draft angles, now in additive manufacturing, we need to consider the printing orientation and design based on that in order to optimize the final part. And finally, if we compare it with sheet metal, we'll move from thinking about which is the folding strategy to make that part work to combine parts together and unify assemblies in order to get the best from the additive manufacturing. So here, one of the messages I would like to transmit today is that it's very important when you are thinking of moving parts from traditional technology into additive to rethink the design and adapt that design to additive so you could get all the advantages that this new technology is bringing to the market. And if we look into the opportunity, there are two main ways to justify 3D printing for end user parts, so for final part production. On one side, one of the reasons to move to 3D is to produce parts that are totally personalized or customized, because that's improving the performance, the ergonomics, and is adding additional value to the customer. One clear area where this personalization is improving the satisfaction, it's in the case of the medical industry, because this full personalization of the products is enabling the patients to get products that are designed for them, which are more comfortable and are easier to use. But this is not the only reason why it makes sense to produce parts or products with multi-jet fusion. There are other cases where the production runs are short or medium size, so the volumes are short or medium, where it makes economically sense to produce the parts with additive manufacturing instead of investing in molds or instead of producing those parts with CNC. The volumes where multi-jet fusion is competitive in terms of economics could go up to the tens of thousands. So it could be 20,000, 30,000 parts per year, and it will depend on the part geometry. And moreover, in this scenario, there are additional advantages of producing the parts with multi-jet fusion instead of using, for example, injection molding. So a part of the cost, we will generate less waste and we will be more scalable because there is no need to produce the molds in advance before you have a total control or you understand completely the demand. So you could scale your production as long as you are learning from the market how that product is performing. And for example, if we compare it with CNC, what we will see is that we are minimizing the waste because we are using an additive technology instead of a subtractive one. And additive manufacturing is a new manufacturing technology and complements the current existing technologies, but it's not the solution for everything. So as it happens with the other technologies, it can be a very good fit for some type of parts. And therefore, the best applications to start multi-jet fusion are the ones you are seeing in the slide. So as I said before, any part with low or medium volume production could be a good candidate. But if we did dive on these candidates, for example, parts where the weight is a limitation are a very good fit for the technology, because in this case, the mass could be reduced. And especially if we are moving parts from metal, so from CNC machining metal to plastic. And in some industries, such as automotive or aerospace, this additional weight is going to reduce the autonomy of an electric vehicle of a drone. So the improvements that you can do in terms of weight reduction can bring additional advantages, such as an additional autonomy. Then, on the other hand, in the fluid management systems, there are a lot of opportunities to combine parts and optimize the performance of the system itself. Today, the geometries that are used in these systems are defined in some cases based on the limitations of the manufacturing processes that are used. And it's very difficult, for example, to get a tube with a variable diameter. However, this is something that we could easily produce with multi-jet fusion because there's a much higher freedom of design. And then apart of that, thanks to the HP's technology, we are able to produce parts that are fluid tight, including fluids such as water, air, etc., without the need of any additional post-process afterwards. And then another interesting area are parts where energy absorption structures may be required. So for example, covers or protections in some sports, including helmets. And any potential opportunity to personalize products is a very good fit of multi-jet fusion. And one good example where we'll see a success story afterwards are customized insoles that are totally manufactured and unique for every patient. And then a part of this, in terms of development time and new product introduction in the market, lead times can be reduced with additive manufacturing, which allows more iterations or faster development cycles. So thanks to this, you will be able to introduce products faster in the market. So you can learn faster, which is the performance and the feedback that you are getting from your customers. And having said this, now I'd like to give you an overview about how multi-jet fusion is enabling these applications today. Today, we see that there's a momentum of 3D printing, and we are in a strong position. So we introduced our first product, our first printer, almost 3 years ago. And from that moment, we have achieved being the #1 commercial thermoplastic solution And a part of that, outside researchers have classified multi-jet fusion and as the most used industrial 3D printer in the market in 2019. And it's nearly 3 times more used than the nearest competitor. Then a part of this, during the sales process in HP, we produce what we call a benchmark, which is an example of the type of application that a potential customer is planning to produce. And what we see is that 50%, more than 50% of those benchmarks today are done for applications that will go into production. So we see that more than 50% of our customers are looking into this final part production. And then a part of that, what this is telling us is that there are new applications that have been enabled across all the different industries, including, for example, automotive, industrial equipments, healthcare, and consumer goods. And as an additional effort, what we are also doing is increasing our portfolio. So during this year, we have introduced a color printer and we have developed and launched a new metal technology. But the reason beyond all those numbers and how we made that possible is thanks to the introduction and the development of multi-jet fusion technology, which is the HP's technology. This is powder based, so we are printing using as a raw material particles of powder, of thermoplastics, and the full process can be divided in 4 different steps. In the first one, the HP inkjet printheads apply liquid agents across the print bed. Then these 2 agents are using during this step as a fusing agent, as a detailing agent. So we have these 2 agents. And the fusing agent is the one that defines the area of powder to be fused. And the detailing agent, however, is the one that is printed on the borders of the part to avoid thermal conductivity to the surrounding powder, which helps to get good part accuracy and then sharper edges. Then after this step, the powder bed is heated by infrared light. And in this moment, water and other volatile components from the liquid agents evaporate. And the particles in the areas where the fusing agent has been placed melt and fuse. And this happens because the fusing agent is provoking more absorption of energy, because it has a higher absorption in a wider range of wavelengths in the infrared region. And thanks to that, the temperature in those areas is higher than in the rest of the print zone. And this enables fusing the material in those areas where the fusing agent is located, while in the rest of the print zone, there's unfused material. And then we repeat this process in each layer. So after we have fused the part, then we apply the next layer of powder and we continue placing the agents and applying the infrared light afterwards. And yeah, why are we using these 2 agents? So this is done because it increases the thermal selectivity during the printing process. So the fusing agent is used to increase the energy absorption of the desired boxes to be made. So for example, if we are printing a cube, we will print fusing agent in a square, in a solid square in each layer. And then on the other hand, the detailing agent is used in the borders of the part to prevent this heat conductivity from the fused parts to the fresh powder in order to ensure this accuracy. So as you can see in this video, for every part, there will be fusing agent creating the final part and the final geometry, and a thin exterior cell of detailing agent applied in the borders of the part. And after explaining the technology, there are also some assets that are used for this printing process that are key to get this final outcome and the performance that we are able to achieve. And one of those critical components is the printhead. So HP uses in the 3D printers the inkjet technology that comes from the 2D printers, and that has been developed for years. And now I'd like to take a minute to talk about some of the characteristics of our printhead. As I said, we have spent dozens of years developing the algorithms for placing the inks where they need to be on a page, and we have transferred this knowledge to the 3D printers. So then if we take one of our printers, which is the color printer, we can see that inside the printheads we have more than 80,000 nozzles. And then the resolution that we have per each of the printheads is 1200 nozzles per inch, which means, so if we combine the quantity of nozzles, the width of the printheads that we used, and the firing speed, we are making more than 2 billion firing decisions per second while a part is being printed. And this is thanks to using the thermal inkjet technology that HP has developed. So previously for the 2D printers and now for the 3D space. And this is one of the reasons why we are able to achieve this high resolution and high level of details, because we have a high resolution in the printheads itself. And now let's see some examples of customer use cases where multi-jet fusion is used today for final part production. So as I said before, today we have customers that are using multi-jet fusion in the main industries, which include transportation, industrial equipment, medical, and consumer goods. So if we start looking into transportation, here we will see that lightweight is one of the critical factors, especially in electric vehicles and motorbikes, because this is going to determine which is the autonomy, or it's one of the factors that will determine the autonomy of the batteries. And here we see that, for example, in the cooling systems, we are able to produce manifolds which have a better efficiency and at the same time have a lower weight. And then apart of that, we also have examples of spare parts, such as the case of the door support that you can see on the bottom of the slide. So this is a spare part that is used in some trains today that has replaced another part that was previously designed to be a metal one, so a sand-casted metal part. So then in order to make that possible, what we did was a redesign of the part to reinforce it to be able to withstand the same quantity of loads, but using plastic instead. Then on the other hand, in the industrial equipment, we are able to produce several parts. So one of those, so two main important areas are the robotic arms and the robotic grips. So here we are able to fully customize each of the grips or the arms based on the final application. Then apart of that, we are also able to reduce the weight of the final end effectors. And by doing this, we are improving as well, which is the efficiency that we have in those robots, because we are moving the gravity center points closer to the arm. So with that, the performance can be improved, and even the motors used to move the arm could be reduced, or the acceleration or the accuracy could be improved instead. And apart of that, we can also use multi-jet fusion to produce tooling, such as thermoforming molds or blow molds. And we have some examples of customers that are doing this today. Then if we move into the medical industry, and here I will show some examples afterwards, we have a lot of examples, because here the customization per each of the patients is key. So we are able to produce the molds for the dental aligners that are used today in a lot of different countries worldwide. Then apart of that, we can produce parts with very good performance and improving the comfort in the orthotics and in the prosthetics space. And finally, we are also able to produce parts in the consumer goods space. So for example, we have some customers that are using today multi-jet fusion to produce virtual reality headsets, chargers. Then in the sports equipment, there are several use cases such as bike helmets. And in footwear, there's a lot of options as well in terms of personalization, like the case of these high heels that you see, or improving the performance and customizing the performance of the flip-flops based on the customer that buys them. And now I'd like to show you an example of a company that is called Bowman that is using today multi-jet fusion to produce their variants. And this is a company that is based in UK and that has been able to develop new designs of their current existing products and innovate thanks to the use of multi-jet fusion technology. Because in this case, due to their volume, it makes economic sense and it's more cost effective.
What we've been able to do is address designs that haven't really changed for over a century and bring 3D printing in and actually massively improve those designs. Bowman is a bearing company. We distribute and manufacture bearings for the entire bearing industry and industrial distribution sector. We started using 3D printing about 3 years ago when we started developing these products and realizing what could be done with 3D printing. For us, the multi-jet fusion process was a massive step forward in terms of output, the number of parts we could make, and the isotropic properties, so having the same mechanical properties throughout the part. With designing for MJF, we're able to design for the optimal product rather than being limited in the geometries we can create. So we're actually able to make the perfect bearing cage in our instance. So for us, PA11 was the obvious choice because it has slightly better mechanical properties, impact resistance, which is important for us, and the elongation of brake, and generally just a slightly higher grade engineering material. By using the MJF cage, we're able to take the entire bearing's load capacity to 30 or 40 or even 50% higher, 3 to 5 times the life of a traditional bearing. There's not a product on the market that comes close to the performance we can get from our product. For us, having the technical support and backup from the HP service engineers is essential to make sure that we can keep our production system running 24/7. For Bowman, we see an enormous future with using MJF technology. What we're doing with 3D printing opens up a whole new world of possibilities. The bearing industry, just on its own, is an enormous industry with tens of thousands, millions of products every year which could benefit from implementing exactly what we've done already with split roller bearings.
Good. So after seeing this video, I wanted to show you as well some examples in the medical industry. Here, there's a new company that is called Small Direct Club, and this company produces clear aligners for correcting the position of the teeth, and it's similar to, for example, Invisalign, which is one of the most known ones. This company started as a do-it-yourself aligner treatment for the front 6 top and bottom teeth. And the way it works and the reason why is do it yourself is because they have reduced some intermediate steps in the workflow or in the process. So now you can go online, fill a questionnaire, and if you are determined to be a suitable case, you can order an impression kit. So this kit is sent to your home. Then you need to make the impression of your teeth, send it back to them, and then they scan that. And there's a doctor that is going to review those teeth and then propose you the different steps that you will follow with the aligners in order to correct your teeth to go into their final position. So then after that, you can order the set of aligners that you will have at your home in a couple of weeks. And all this process is costing the patients around $1,800, which is a big difference compared to any other treatment, aligners treatment that is today available in the market, which are or which have costs that are higher than $5,000. So they are driving the cost down both in the production of the aligners and at the same time making easier to access to the patients and removing some intermediate steps. So today they have 49 multi-jet fusion printers and they produce more than 50,000 unique mouth molds per day. So they are going into high volume production in this application. And then if we deep dive in the other areas in the medical space, then we see that there's a lot of opportunity in the prosthetics and orthotics. Here, for example, in terms of productivity, we are able to produce parts faster compared to other traditional methods and compared to other 3D printing technologies. But at the same time, as in most of the cases, the way to produce the final parts today, it's a very manual process. We are able to reduce a lot this manual labor time. Then if we take a look into the quality of the parts, so the reason why we are able today to produce insoles in orthotics and in the sports industry, it's because with our HP's technology and with our materials, we are able to produce isotropic properties, which means that the parts are going to have the same behavior no matter the printing orientation. So this is enabling having these high performance products and being able to withstand fatigue and a number of cycles, for example, in the terms of insoles or any other prosthetics and orthotics product. And a part of this, we have passed the biocompatible certifications to have contact with the skin. And then if we look into the third pillar, we are also more sustainable than other traditional technologies or traditional processes. So for example, we are able to reduce the waste up to 20 times in the insoles production if we compare it with CNC machining. And a part of this, we have high reusable materials and our PA11 is coming from a renewable source. So it's made from castor oil, which make it a renewable material. And if we look into the potential applications where we see our best fit in terms of orthotics and prosthetics is in the insoles. In this case, we can modify the stiffness of the insoles based on the customer and the ergonomics, and we can personalize it for each of them. Then a part of that in braces, DAFOs, and cranial orthoses or helmets, we are able to produce parts that are less bulky and that are lighter, so they are more comfortable to use. Then in the sockets, we are able to improve as well the ergonomics. Mainly in the sockets, this is a big thing because this has to be in contact with the patient directly, and it has to be comfortable because it's going to withstand a lot of load coming from the weight of the patient. And in the fairings, for example, we are also able to produce parts that are more cost effective and that can be unified from other combination of parts that have been produced in the past with other traditional technologies. But in all these cases, if we take a look into the numbers, so we are also very cost effective. So we are improving the ergonomics, we are improving the performance of the patients, but at the same time, we are providing a manufacturing option that is more cost effective than the traditional options used today, and that it's faster in most of the cases. So here you could see a reference of the range of prices that we have for each of these applications. And here, this number is including both the variable and the fixed cost, which includes the hardware amortization, the maintenance contract, the maintenance kits that are required, the materials and the agents that are used to produce these parts. So it's taking into account the full cost of the process. And obviously, if you have an application where you see you would like to evaluate the cost, we are more than willing to run a cost calculation for you with your specific example. And now, if we look into some into the companies that are using this today, we have, for example, Invent Medical, which is a European company that is producing today orthotic insoles with multi-jet fusion with the HP PA12. Here, the main advantage that we have obtained from moving their current process to additive manufacturing is that before they tried other 3D printing technologies, but it didn't work because in the technologies they tried were not isotropic and they were not providing the final quality that they required. So until today, they have not been able to move into production with 3D. And now, thanks to multi-jet fusion, they have done this final step. And now I'd like to show you another video where you could see how they make that happen.
I started working out with personal coach and I started noticing some pain in my feet.
With interactive configurator and 3D printing technology, I am able to design truly custom, perfectly fitting orthotic insoles.
With multi-jet fusion technology, we are able to design and print out directly the final product to make the product lighter, more comfortable, flexible, and to higher its performance.
After I got my first insoles, I was really surprised because I was able to run almost for an hour without noticing any pain. I can fit them into any of my shoes and don't even notice them.
We believe that with 3D printing by HP, we can disrupt the whole industry by providing patients all around the globe with new advanced products that can improve their lives.
Good. And after this video, I'd like to show you my last example of a final part production today. And this is the case of Hulotech, which is a company that is producing parts for additive manufacturing, and it's also an engineering company that is specialized in medical production, or the production of some medical applications. And in this case, one of the things they have started to produce with our technology are the sockets. So in the sockets today, if the problem that they have is that with the traditional process, which is normally producing these parts with plasters, they end up having products that are very heavy. They have a poor durability, and the most important thing is that they are not comfortable for the patients. And a part of that, when one of these sockets is produced and it's tried by the patient, they need to do some final adjustments in most of the cases in order to make it totally fit. So now they have moved into multi-jet, and they have been able to overcome all these problems they had in the past. So the parts they produce today are lighter, they have a better durability, and they have also improved the comfortness of the patients because the parts are more adapted to the final customer, and they don't need to do all these final adjustments that were required in the previous process. And as the last video, I'd like to show you the testimonial of one of the patients that is using a 3D printed socket today.
I had an amputation when I was 1 year old, and so since then I've had so many prosthetic legs.
My patient lost his leg when a traumatic accident, and he came with a wish to walk again. So we make a socket as an interface for his prosthetic foot.
What HP has solved for us is the quality of the products.
Unlike previous experiences I had, that I had to fit the socket a couple of times, could take sometimes weeks, in some cases months, to get the final fit. This one was perfect fit the first time.
Main reason Hulutech invested in this new MJF technology was the fast production time of parts. Today the order, tomorrow they will use it on their patient.
I believe that this technology is a good step towards future when we as patients can get the results very quick and see that we can comfortably go back to life without waiting and sitting until the solutions are ready.
Good. So this is the last video and the last slide I had in my presentation. So yeah, thank you very much for attending this webinar. I hope it was useful. And now I will let Andy to start with any question that you may have and having some additional information for you.
Thank you, Isabel. So give me one quick second here while I switch back to screen. So while we're waiting for the questions to come in, and by the way, there were a couple of questions that came in, but if you have more questions, please feel free to type into the Q&A panel right now, and we will address them. But I just want to remind everyone of upcoming events that we have around 3D printing. If you happen to be in the Southern California area, in Orange County, next week we have a seminar specifically focused on prosthetics, orthotics, and mass customization. You get to see the machine, some of the parts. There's more interactive information, obviously, if you're there live. So if you're around the area, I highly recommend joining us next week. And then we also have a webinar focused on design for additive coming up in August, and an event in Texas. So if you're in the Texas area and you want to learn more about HP Advanced Manufacturing, that's please come join us. Just log on to saratech.com and then click on the events menu button, and you see all of these events up there that you can register for. So Isabel, those are a couple of questions that came in. David had a couple of questions. One is, what % of material can be reused, and how much new material must you add to it?
Good. That's a very good question. So our here we have materials that are highly reusable, and the material that you can recycle the most is the PA12, where you can recycle up to the 80% of the material in each job. So that means that for each new job you are going to print, you are able to put a 20% of fresh material and 80% of recycled material without impacting the mechanical properties. So we assure the same mechanical properties with this mix. And in the case of the PA11, the mix ratio is 30% fresh material and 70% recycled material.
Great, thank you, Isabel. David also had a follow-up question regarding proper protective equipment required. So he saw in the video that people were wearing glasses, but the material is fine powder. Are there any respirators or special equipments required when running these machines?
Yeah, actually, there's no requirement for any specific protection equipment, but for the comfortness of the operators, they could wear it. But we are assuring that with our powder, we have particles that are not in the particle size where this can be harmful for the health of the operators, of the people that is surrounding the printers. And we have white papers with that information that we could share in case there's someone that is interested in more details about that.
Okay, perfect, Isabel. Thank you so much. I know that we're come to the end of our webcast. Really appreciate your time. I do want to remind the audience that as you log off, there's a short survey that pops up. Only takes you a minute to fill that out. Only 5 questions. As a thank you for filling that out, we will send you a white paper on HP MJF technology with a lot more detail than what you saw today. And also, don't forget to follow us on social media. That's where we make our announcements, post our videos and webcasts. So please take a minute to follow us on social so you are always up to date on the latest technology. With that, thank you everyone for joining us today, and thank you very much, Isabel, for taking time from your busy day to present. Appreciate your time.
Yeah, sure, my pleasure. Yeah, thank you very much, everyone, and have a good rest of the day.
Thank you.